Hey guys, welcome to day 34. We're going to start taking a look at related rates here. What a related rate type of problem is generally these are actually kind of a throwback to some geometry. But what we have is we have a shape, either 2D or 3D, changing in some way, and we know that rate. And what we want to do is figure out how other aspects of that shape are changing at the same time, because they're related, but they are not the same. So hence related rates. I'm going to give you a quick list on some strategy, just kind of a way to organize your thinking on this. It's very important to follow these steps because it'll just help us guide our thinking towards the correct answer and make sure we catch everything. In these related rate word problems, the first thing we have to do is we want to make an organized list of what we know. When we're talking about things we know, we want to differentiate between rates and amounts. An amount will be a simple unit, such as centimeters or centimeters squared, or something like that, whereas a rate will be that divided by time, so centimeters per second. Square centimeters per second, cubic centimeters per second, something like that. So we're going to have to keep track of those. The second thing is we want to write down what we need. Look for the question words in the problem, like what is the rate of change of the area, or what is the rate of change of the circumference, or what is the rate of change of the volume. Those question words kind of help guide us towards what we're actually supposed to solve for. Okay, write down what you need, and again, careful with a rate versus an amount. So after you've listed what you know and listed what you need, what we need is an equation that relates the two together. Now, sometimes you're responsible for knowing what equation relates these things. Sometimes they will provide an equation for you. For example, if it's about the area of a rectangle, you need to know the equation area equals length times width. You need to know the Pythagorean theorem. You need to know area of a triangle. We need to know all those simple things. You'll kind of see which ones you're going to be responsible for knowing. And but things like surface area and volume of a sphere will be given, cylinder stuff will be given, cone stuff will be given. And then sometimes they just make up shapes and make up equations. Obviously, those will be given as well. Okay, so after we write our equation that relates what we know and what we need, the fourth step is we need to do the derivative. Can I put implicit there in parentheses? We treat everything like it's an implicit differentiation, where kind of like everything is the y value, right? So if you're doing the derivative of r squared, it's going to be 2r and then dr dt. Okay? So we're always tacking on the derivative when we're doing it. Okay, and then fifth, solve for what you need. occasionally too, after you derive and solve for what you need, you might find that you have two unknowns. Okay, so we need to go back to our know list and see, was there anything we could have added to our know list? Sometimes they give you a piece of information that isn't directly what you need, but can be related to something directly that you need. I'll show you an example of what I mean by that. Okay, so let's take a look at, I'm going to show you 3 examples. Okay, so here's the question. You want to just pause the video quick to make sure you copy down that question into your notes. Okay, so here we have, I said, a circle is expanding. The radius is increasing at a rate of 3 centimeters per second. What is the rate of change of the area of the circle when the radius equals 9 centimeters? Okay, so let's get an idea of what's going on here. So what we have is a circle, and that circle, that circle is expanding, okay? So the radius is getting bigger at a constant rate of 3 centimeters per second. Okay? Well, as that circle is getting bigger, we can tell that the area of the circle also is going to be getting bigger. Okay? And we want to know how much, like what rate that area is getting bigger. We don't care about the area of the circle, right? That's a very 9th grade, 10th grade, 8th grade type question, right? The area of the circle is 81 pi. That's not a big deal. Okay, but what I want to know is how fast is that area changing? How much is that area growing by? Okay, which is a much more difficult, but also more interesting question. Okay, so I'm going to move this circle out of the way here. Sometimes drawing a picture helps too. If you need a picture of a circle to know what it looks like, go ahead and draw one. If you don't worry about it. So the first thing we want to do is write a list of what we know. Okay. So there are 2 things that I told you, and both of them related to the radius. But again, I said we needed to pay attention to the difference between a rate and an amount. So it says the radius is increasing at a rate of 3 centimeters per second. That is very clear that that is a rate, because I use the word rate. Also, if you take a look at the unit there, 3 centimeters per second, right? It's growing 3 centimeters every 1 second. So over time, every second that passes, the radius gets 3 centimeters bigger. So I need to show that that's a rate by listing it as a derivative. And all of our derivatives in this unit will be with respect to time. And since I'm dealing with a radius here, I'm not going to use r equals 3. I'm going to use the derivative of r with respect to time equals 3. And that's going to look like dr dt. dr dt. When I make my know and need lists, I don't include units. My final answer should include units, however. Okay. The other thing I know is I want to it says when the radius equals 9 centimeters. Okay, and we notice 9 centimeters, that's simply our radius value. So here I'm just going to write r equals 9. Those are the two things that I explicitly know. I gave you the rate of change of the radius, dr dt, and I gave you the instantaneous radius length of 9 centimeters. Okay. There are other things that I could know, though. I could know the area at that instant. I could know the perimeter at that instant. I'm not going to write them down, but in case I need them, maybe later on I can find them if necessary. Okay. The next, so I've got my complete no list, at least for now. Now I'm going to write what I need. I look back to the question here, question word. The question word is what? What is the rate of change of the area? So what I need is not the area of the circle, but the rate of change of the area. Now, if the rate of change of the radius was dr dt, what would make sense for the rate of change of the area? Well, of course, that'd be dA dt is what we're looking for. Very often our need will be a rate of change. Not always, but often our need is a rate of change. Okay, and the last thing I have to do here, or the next thing I have to do here, is find an equation that relates what I need to what I know. Well, again, I need information about area, and I know information about the radius. This would be an example of an equation that you will be expected to remember on the test, and we know that the area of the circle is equal to pi r squared. So that's our equation that we're going to work with. And again, just as a reminder here, pi is simply a constant. Right? We know it's approximately 3.14, but it's just a constant here. But I do have variables. I have a variable r, and I have a variable a, and I'm going to be deriving everything by the variable t. Okay, so let's get into the next step. Step 4. Oh, by the way, don't plug any numbers into your equation unless they are constants. Right? I don't have any constants here other than pi. A is going to be changing, r is going to be changing, so they're going to remain variables until after I do the derivative. That's when I'm going to plug in and solve. Okay, so step 4 is do the derivative. And again, I'm going to treat this like implicit differentiation. The derivative of a is 1, but I need to multiply on my dA dt. So I'm just going to write that as dA dt. I'm going to go ahead and derive both sides of this equation. The derivative of a is quite simple. It's just dA dt. The derivative of pi r squared is going to be 2 pi r. But again, I need to tack on dr dt. Right? That's where it's like similar to implicit differentiation. So the derivative of pi r squared. By the way, I don't need the product rule because I don't have two variables. Pi is not a variable. I have one variable with a coefficient and an exponent. So the derivative of pi r squared, I'm just using the power rule, multiply the 2 out front, and I'm going to get 2 pi r to the first, and then multiplied by dr dt. Now I just need to plug in and solve for what I need. What I need is dA dt. So it's okay that I have nothing to plug in for dA dt. But I should be able to plug in everywhere else in this equation. And when I look, 2 and pi are constants. I know r and I know dr dt, so this should be very straightforward. Let's say dA dt equals, Again, this is why it's nice to have this no list over here, because they're just really easy, well organized to plug in to make sure you plug in the right things. R is going to be 9. dr dt is going to be 3. And multiplying those out, I'm going to do 2 times 3 first and get 6. 6 times 9 is 54. So my dA dt then would be 54 pi. My unit now, to figure out the units here, just think about what the unit of area would be. Well, I gave things in terms of centimeters here, so an area would be centimeters squared. Think about our T unit on the bottom. Our T unit was in seconds from up here. Oops. Double check that. All right, we are dealing with centimeters and seconds, as we can see in that rate of change there. So our unit will be centimeters squared per second. That's our final answer here. Okay, let me show you a new problem. Okay, so again, here's the problem. A rectangle is changing dimensions. The length is increasing at a rate of 4 centimeters per second, while the width is decreasing at a rate of 2 centimeters per second. Find the rate of change of the area of the rectangle when the length is 10 and the width is 6. Throw units on there, centimeters. Okay, a couple of things to pay attention to here. We have both the length and the width changing, but we really need to pay attention to words like increasing and decreasing. Hey, just like our last unit. If a rate of change, if a dimension is increasing, then we know our rate of change needs to be positive. Whereas if a dimension is decreasing, we know the rate of change needs to be negative. You have to pay very close attention to that to make sure, right? It's easy, if you're just looking through and picking out numbers, it's really easy to miss that word decreasing and that word increasing. So again, let's make a list of what we know. I know the length is increasing at 4 centimeters per second. So what that is obviously a rate. We can tell that by both the units and the use of the word rate. And I know that the length is increasing, so I know I'm going to have a positive 4 rather than a negative 4. To write this in my no column then, since it's a rate, and I'm talking about length, I'm going to call it dL dt. Now the width is decreasing at a rate of 2 centimeters per second. So it's talking about the rate of change of width, so I'm going to use dW dt. And the key here is that dW dw dt equals negative 2. Okay? Very important to see the difference there. All right, then lastly, I also know amounts, right? I know we're talking about the instant the rectangle has a length of 10. So I know L is going to equal 10. And I know W is going to equal 6. Our dimensions are always going to be positive. We can't have negative dimensions in a real world problem. But we can absolutely have negative rates in a real world problem. Okay. The question then is, what do I need? All right, so we're trying to find the rate of change of the area. So once again, my need is going to be the rate of change of the area. So I'm going to call that dAdt. Okay, and I'm going to find I need to think of an equation here that relates area of a rectangle to length and width of a rectangle. Again, this would be an example of something you need to know. Area equals length times width, right? Or base times height. Whatever you end up choosing for your equation, make sure the variables match what you've listed in your no column, right? If I do area equals base times height, I'm going to be really confused when I have this L and W sitting over there. Right? So even if you know that an equation, right, or let's say Pythagorean theorem, a squared plus b squared equals c squared. But if you use the letters x, y, and z for your no column, right, you're going to confuse yourself. So be consistent. Make your equation match the types of variables that you used in your no column. So here we have it. Area equals length times width. Now, all three of these are variables. Once again, the left side of the equation will be easy to derive. But what are we going to need to do on the right side? Well, what I see there is a function times a function, length times width. So in order to do this derivative, I'm going to have to do the product rule. I also need to remember that I'm doing this like I do implicit differentiation. Okay, so let's start with the derivative on the left side. The derivative of A is 1 dAdt. I'm just going to call that dAdt. Now I have to do the product rule. First, second. I'm going to start with the derivative of the first. The derivative of L is 1. But again, I need to tack on my dL dt. So I have the derivative of the first times the second, plus the first times the derivative of the second. The derivative of W is 1, but I need to tack on that dW dt. There I have a proper derivative. And again, I can look through my no column here, and I should be able to plug in for everything except dAdt. By the way, it was really obvious in our last problem that the area of the circle would be increasing as the radius increased. But here I have part of my rectangle increasing and part of it decreasing. So it might not be intuitive right now, right? We're going to have to do this analysis to figure out if the area of this rectangle is actually getting bigger or smaller. Well, we'll be able to answer that question when we look at the sign of dAdt. If dAdt is a positive number, the rectangle area is increasing. If dAdt is less than 0, then I know the rectangle is decreasing in area. If dAdt equals 0, then it's staying the same. So let's go ahead and solve this thing and be done. So again, I have my nice list to plug in. dL dt is 4, W is 6, plus my length is 10, and my dW dt is negative 2. Solving this out, 4 times 6 is 24. Minus 20, which equals 4. Unit here, my area unit would be centimeters squared. My time unit would be seconds. So since I got a positive number here, the area of this rectangle is increasing at that instant. Okay. Now, if I change the rates, that could change. Also, if I changed the amounts, right, the time in which I'm checking that, we could also change that as well. Okay, we'll just look at those two examples. Have a great Thanksgiving break. I will see you guys on Monday in December. 2 Chainz, bye.